Welcome to Homework Lib.
Chapter 14, question 124. The NOx waste stream from an automobile exhaust includes species such as NO and NO2. So this X stands for 1 and 2. Catalysts that convert these species to N2 are desirable to reduce the air pollution. Draw Lewis dot and VSEPR structures for NO, NO2, and N2. So let's first draw all these three structures. For NO, what we need to do is we need to count the outer shell electrons. So how many we have for nitrogen? It's in 5a, so there are 5 electrons. And for oxygen, it's at 6a, so there are 6 electrons at the outer shell. So usually we draw one line, and this is going to be the VSEPR. We draw a line and then we start assigning the electrons. We have a total 11 electrons. So 2 we used, so we need 9 more. Let's go with oxygen. There are 2, 2, 2, 6, 7, 8, and 9. Now, this is not a good way to show this because we also need a little bit of the octet rule to apply to. Why I say a little bit of? Because it's not going to make this nitrogen a complete octet, but it's going to be a 7 electrons. How we can do that is if I move this over here. So what am I going to get? Let's count the electrons again. 2, 2, 2, 6, 7, 8, 9. Oh, we need 11. So we need 2 more electrons. So this is going to become, if I merge these 2 electrons, nitrogen, 2 electrons, 1 electron, 2 bonds, and an oxygen, 2, 2. So let's count again, 11, 2, 4, 6, 8, 10, 11, 11 electrons. So this is a good VSEPR. Now, if you want to convert this to the Lewis structure, it's very simple. What you want to do is draw the same molecule, except for each bond, you just want to show it as 2 electrons. So this is going to be the Lewis structure. Let's do that for NO2. The N is going to be the central atom. So I'm going to first draw it like this. And again, there's 5 electrons for nitrogen, 6 electrons for one of the oxygens, and 6 electrons for the other oxygen. So how many electrons we're going to get at the end is going to be 6, 6, 12 plus 5, 17. So let's try to draw this. I'm going to just assign 6 over here. So we need 11 more. Minus 2, 9. Minus 2, 7. We need 3 more. What about this? So let's look at the octet rule and what we can do to make this picture better. There are 6 electrons around this oxygen. So I can as well just get these electrons over here and put this single one over here. Now, again, this does not look good because nitrogen has 4, 5 electrons. At least it needs 2 more electrons. So how we can fix is if I merge these 2 electrons over here, what I will get is going to make all the atoms happy. Let's count the electrons again. 2, 2, 2, 6, 8, 10, 12, 14, 16, 17. And how many electrons we have around nitrogen? 2, 2, 2, plus 1, 7 electrons. So this is not bad. It's the best we can assign for a nitrogen at this configuration. Now, how does this look like? Well, normally an electron pair would push this two atoms down. It's not an electron pair, but it will still push this two bonds down a little, and it's going to look like a bent-shaped molecule, like this. And the Lewis structure for this is going to be, again, if we get just the electrons instead of the bonds, and over here, just one bond, and the electrons, and one more electron, and this is going to be the Lewis structure. And lastly, N2. Now what we have is two Ns and 5 electrons from one and 5 electrons from the other. So we're going to have total 10 electrons. Now there's 2, 4, 6, 8, 10. If we count them, just look at one of those nitrogens, 2, 4, 6. So it does not look very nice. What we can do is let's try to merge the electrons and see what happens. If I merge these two, then this is going to be N, 2 electrons over here, a triple bond, another N. That was an ugly N. Now this is a more beautiful N. And now if we count the electrons, 2, 2, 2, 2, 2, 10 electrons. And every nitrogen has 2, 2, 2 plus 2, 8 electrons around. So this is a good structure. And for the Lewis structure of this guy, again, we're just going to do electrons rather than the bonds. And this is going to be the Lewis structures. So let's write VSEPR over here and Lewis over here. Now, using a resource such as table 8.3, right over here, look up the energies of the bonds in these molecules. So first off, what we need to look at is, let's look at N double bond O. Let's look at this NO. Can we see it? It's going to be here. This is going to be 607. What about this guy? And one single bond and one double bond O. So this is going to be 607 plus NO 201. So this is going to be 808. And these are in kilojoules per mole. And lastly, N3 is right over here. This is going to be 941. In what region of this electromagnetic spectrum are these energies? So how we do that is going to be our formula E equals to hc over lambda. And what is E? E is going to be in joules. H is going to be in 6.626 times 10 to the power of negative 34 joules per second. C is approximately 3 times 10 to the power of 8 meters per second. And we need to find the lambda. Now, if we use the energies 607 for NO and solve it for 600 for the lambda using 607, and for NO2 if you use 808, and for N2 if you use 941. Now these are kilojoules, so you want to add 1,000 to make it joules. And lastly, don't forget the lambda value you're going to get is going to be in meters, but you want to look at nanometers. So to convert meters to nanometers, what you need to do is this is the multiplication factor between these two. So once you get the values, what I have over here is for NO, we have 197 nanometers. For NO2, we have, let me check my notes, please. It's going to be 148 nanometers. And lastly, for this guy, N2, we will have 127 nanometers. Now, the last question is asking, design a spectroscopic experiment to monitor the conversion of NOx into N2. So first of all, what electromagnetic spectrum we are is going to be, this is all these values are ultraviolet. These are just above the visible spectrum, and visible spectrum is between 400 and 700 nanometers, and these are just above, so it's going to be ultraviolet. And to do this spectroscopic experiment, what one should be looking at is, this is the important value, 127, and one should be looking at this value, and the other values are going to be 148 and 197. So they want to look at these values to drop down to value of 127. So one can safely say that these NO and NO2 are converted to N2 values.